Good afternoon, everyone. Today we are going to be building a machine learning model from scratch. Now, the goal of this model is to be able to tell with reasonable accuracy if an inputted image is an image of a dog or not. Very simple. It's a binary yes, no. Its sole job is to tell if an image that we input is an image of a dog or not. By going to Google Colab, this is where we'll be coding everything. As you can see, I've already made a practice notebook, ML practice. So here we are. This is where we're going to be starting the coding session. Now, the first thing that we want to do is go here to runtime and change runtime type. And we want to switch from the CPU to the T4 GPU. Why is that? Well, GPUs are much better for handling the type of calculations that are behind ML. So machine learning and this type of stuff that we're going to be coding today, it essentially does a lot of matrix multiplication. Those are the calculations that are underlying beneath the surface. And GPUs are much better with thousands of calculations. You can think of a CPU as a couple brilliant mathematicians working together, whereas GPU is thousands of arithmetic clerks. Right? Not as genius on an individual level, but much better at doing a lot more and denser problem sets. So we're going to save. And our first cell is just going to be opening the main toolbox, import torch, and we are going to confirm that the GPU is indeed working. So we're going to print the statement, GPU available, torch.cuda.is underscore available. So this is just asking a question of, did we get the GPU, right? Are we using the GPU for what we want to be doing later? And again, we want this statement to be true, right? Torch CUDA is available. We want that statement to be true rather than false. That means the GPU is available and we can proceed. Another thing that I'd like to say before we continue is that this video is intended for absolute beginners, people who are interested and curious about machine learning and want to apply principles that they've heard about, maybe on social media, news, from their own research, but are maybe unsure of exactly how to implement it and the specifics of the code. So I'm going to go through this very slowly and explain each part as best I can for absolute beginners to understand and have a working model by the end of it. So we're also going to print device torch CUDA get underscore device underscore name 0 if torch dot CUDA dot is underscore available, else CPU only. Alright, so again, this is all the first cell is, and essentially this is just confirming that the GPU is up and running. So we're going to go ahead and run the cell, and again we should see the GPU is available. It might take a second. And there we go, GPU available, true, and the device used is Tesla T4. That's just the type of GPU. That's not important. All we wanted to know is that this is up and running and good to go. So now that we know that, we can proceed to the second cell, which is essentially just writing out the tools that we're going to use to build the model, right? So we're not constructing our own tools from scratch, we're importing tools. Think of what we're going to import as, the hammers, screwdrivers, all of the tools required to build the structure that we are going to build. So, import torch.nn as an n from torch.utils.data import data loader import torch vision from torch vision import transforms models and import numpy as np. So again, these are just the toolboxes that we're going to use, the tools that we're going to use, and importing these things is opening the toolbox, getting us prepared to build what we're going to build. Next, I'm going to do device equals torch.device CUDA if torch.CUDA.is underscore available else CPU. Now, why are we doing this? This is just writing down which chip we're using, and it saves it under the same name, device. So we can essentially say to the program, put this on the GPU if we're using the CPU, without repeating ourselves. And another important thing to know is the program and the photos that we're going to be importing have to be on the same chip or nothing works. So this is just keeping that straight. Now, next we're going to input some numbers here, and I will explain what exactly they mean after we write them out. 4, 5, 6, 4, 5, 6. Alright, so these numbers, they don't have any meaning to you yet, but they're not just arbitrary. They are, obviously, mean is mean, or the average value, and ST stands for standard deviation. They describe the average brightness of red, green, and blue across the millions of photos that the program we're borrowing from originally studied. So essentially, any photo that we input, we're going to be changing the red, green, and blue of the photo using these numbers to match as close as we can to what the model already knows. So it's more likely that the model will be able to understand the image better and give us a better prediction, which is obviously what we're looking for. All right, so now we move on to train underscore TF equals transforms dot compose, and here we're just starting a recipe for preparing the practice photos. And all this compose means is just to do these steps in order. So this is the training portion, essentially. Transforms dot resize 224. Transforms dot random horizontal flip transforms. Don't worry, I'll explain what each of these means once we're done writing all of them out. Oops. Transforms dot normalize mean standard deviation, and closing brackets. Okay. So again, this is in our training here. So this resize 224. Why are we doing that? We're doing that to make every photo the exact same size. So any photo that we import or any photo that the model is training on will be the exact same size. Right? The borrowed program that we're using expects one specific size and may get confused by anything else. It's like a machine that only accepts a certain type of paper. Right? To be able to perform to the best of its ability, we want to give it things that it recognizes, and we don't want the dimensions of the photo to mess up the model's accuracy. The other transforms random horizontal flip. This randomly flips about half of the practice photos from left to right. Now, why do we do that? In any given photo, a dog can be facing to the right or to the left. It doesn't change the fact that it is still a dog, and we don't want the model to only train on dogs facing a certain way and start to make the false correlation that the orientation of the animal means that it's a dog. So about half of the practice photos are flipped, so the model can learn that the orientation doesn't matter and actually have it analyze the specific animal and its physical features to determine whether it's a dog or not. Transforms to tensor. This just turns the photo into pure numbers. Right, so the program doesn't have actual eyes. It can't look at a picture. It can only do arithmetic. So essentially we're translating the photo into a language that the model can understand for it to dissect the photo and analyze it, and every pixel in the photo will become a number. The last one transforms normalized mean STD. We talked about this before. This is just using the 6 numbers above to adjust the brightness and color balance so it matches what the borrowed program is used to. And obviously this closes the recipe. So we can move on to test underscore TF equals, and before we proceed, I can explain one more thing just so you don't go typing blindly into this. You have an idea of what we're doing. There are 2 sets of training the model, really. There's actually training the model and then giving it exams or tests, right? So in training, the model goes through these photos, and that's what train underscore TF is for. Test underscore TF will be for when the model is taking these exams to prove that it has learned something, so it can move on and we have a proof of concept, or it's giving us a reasonably good accuracy at assessing whether a photo is a dog or not. So it's going to look pretty similar to the train underscore TF, but slightly different. Pose. There we go. Sorry about that. It seems that I forgot a comma there. Comma at the end of transforms resize. Make sure you get that. My apologies. So again, opening, similar recipe, but it's not going to be exactly the same. So we're still going to resize the photos to 224 pixels. Again, that's what the model is used to. We're still going to have to translate to the model, translate the photos into a language that the model understands. And finally, we are going to adjust the brightness so that the model still recognizes it. Again, the only difference here is that there's no random flip. So the practice photos are getting shuffled to make the lesson more difficult, and the exam photos stay untouched, so the model's getting both of those ideas. What's going on here? Anyways, the model's getting both of those ideas, both of those test sets, so we can see more things. Alright, so that's going to do it for cell 2. Don't worry about this. This is still the syntax error of me forgetting a comma. So we can move on to cell 3. And we're going to write out all these cells. There's 7 cells total, and then run them all. but you can actually run each one individually. Like you can run this to make sure and see this check mark means that everything's good. But once we get to actually training the model, not just setting up the parameters for training, it will take a little bit. So I'm going to write all of the cells down and then hit this run all. And that's what I recommend that you do, so you have everything written out. You don't have to keep stopping and waiting in between. So, cell 3. This is, and you know what, I'm going to start adding little comments up here. Getting the photos and stacking the deck. So this is the cell where we actually extract the photos from the internet and feed it to the model, and also making sure, essentially taking luck out of the equation and making what the model guesses as the only factor in seeing how accurate it is, right? Because we don't want the photos to be shuffled in a certain way where our model seems better or worse than it actually is. So, full train equals torchvision.datasets.cfar10 root equals dot backslash data. I'm sorry, that should be ROOT. Train equals true. Download equals true. Transform equals train underscore TF and parentheses. And you can probably guess that the next line will be full test equals torchvision.datasets.cfar10 root equals dot backslash data, comma, train equals false, download equals true, transform equals test underscore TF. Now, these two lines are downloading a free public collection from CFAR, a Canadian organization very well known in the machine learning or computer vision space. We're downloading a collection of about 60,000 small photos, and it arrives pre-split into practice photos, which is the first line, and exam photos, which is the second line, and the two piles stay separated forever. They never overlap, which is important because we want the model to be tested on different photos, right? So we can make sure it actually learns. When you're in school, if you get a practice exam, the actual exam, same concept of questions, but different, not word for word questions, because you could just memorize the answer to the question. Now for the simplest line, and I messed it up, but the simplest line for all of today, dog equals 5. Now I guarantee that you have not heard that in your math class, dog equals 5. Why are we doing that? Well, because the categories are numbered rather than named, and dogs happen to be the number 5. So this data set has a bunch of different categories for different objects and animals, and essentially we're just making this more readable for us. Like I already mentioned, the model, it just communicates and does things through arithmetic. So we're just giving the fifth category, which is dog, we're labeling it as dog, so when the model's talking about it to us, it'll return dog. And just, I thought, a quick mention, cats are category number 3, which will come up later. Now, def, make binary, base, comma seed, equals 42. So what this line does is it starts a reusable routine whose job is to pick which photos we keep. right? And this C equals 42 just means to shuffle the same way every time. So we're taking luck out of the equation, right? If we run it tomorrow, we get the identical selection, and any change in the score comes from something that we changed, not just the luck of how the photos were shuffled. And we can go targets equals np dot array parentheses base targets dog underscore idx equals np dot where parentheses targets equals dog bracket 0 bracket non-dog idx equals np dot where targets do not equal dog bracket 0 bracket. So what these three lines do is they grab the list of what every photo is and then make two lists, what the dogs are and what everything else is. So considering we have so many categories, right, we have 10 categories, as of right now that would mean that we have 5,000 dogs and 45,000 not dogs, which is a problem that we'll address later. We're about to get to it, obviously. But while we type this out, I'll let you think about why that could be an issue if we have so many more not dog photos, 45,000 non-dog photos and 5,000 non-dog photos that the model trains on. RNG equals np dot random dot defaults underscore RNG seed non-dog underscore idx equals RNG dot choice non-dog underscore idx size equals len dog idx replace equals false. Alright, so these two lines address the previous problem that I just mentioned. This is arguably the most important part of the cell, so it throws away most of the non-dog photos, and it keeps only as many as we have dogs. So 5,000 dog photos, 5,000 non-dog photos, as opposed to 5,000 dog photos and 45,000 non-dog photos. Why bother, right? Well, only one category in 10 is dogs, like we mentioned. So if we used everything, if we used all those photos, 90% of the photos would be not dog. So a lazy program could learn to just answer not dog every single time and score a 90% accuracy. And we might be looking at that and go, wow, our model's great. I mean, we've done something really well here. When in reality, the model hasn't learned anything. All it's doing is clicking the same answer, and because our data set is so skewed, the accuracy number is extremely unreliable, and our model is not actually 90% accurate at assessing whether a photo is a dog or not. So that's why it's so important to be able to procure and set up your data, not only extract good data, but to procure it in a way that takes any bias or luck out of the equation and really leaves it all up to the model determining whether an object is a thing or not. In our case, determining whether an image shows a dog or a non-dog. So we're forcing 50-50 here, which means the model guessing will get us about 50% every single time. And anything above that, we know the model is actually learning, actually analyzing the physical traits of the image and determining whether it's a dog or not. So we move on to return np dot dog underscore idx non-dog underscore idx bracket parentheses. So all this does is return or hands back the combined list of 5,000 dogs and 5,000 not dogs. So this is just a continuation of the last two lines. Def underscore init self, comma, base, comma, indices, self dot base, self dot indices equals base, comma, list indices. And we have def len self return len self dot indices. So all this code is doing is setting up a small helper which just hands the photos over one at a time when asked. Alright, so the first part of this remembers what collection and which photos we chose, and the second part can report how many there are. There's no real ideas or analysis going on here. This is basically the plumbing of the model that we're setting up, right? It's just the boring part that's necessary to get everything to work. So, def get item underscore self, comma img, comma label equals self dot base, self dot indices I. Return img, comma 1 if label equals dog, else 0. So that line that I just wrote does the relabeling. So when asked for a photo, it fetches it, it checks its original category, and says 1 if it's dog and 0 for anything else. Right, so this is essentially collapsing 10 categories into 2, either dog or not dog, which is what the model is going to do. Again, 1 for dog, 0 for anything else. And the photo remains untouched. It's just the label that changes. So now we can move on to setting up the training. Train underscore ds equals binary dog full train, comma, make underscore binary full underscore train test underscore ds. Again, one for the training section, one for the test section. Binary dog full underscore test make binary full test. So this is, again, just building the two balanced piles using everything above, the two piles being the practice pile and the exam pile. Alright, now we have train loader equals data loader. You can probably guess that these lines are going to be loading the data. Train underscore ds, batch size equals 64, shuffle equals true, num workers equals 2. Test loader equals data loader test underscore ds, comma, batch size equals 64, shuffle equals false, num workers equals 2. Alright, so this is essentially, like I said, loading the data or setting up the delivery system. So this batch size equals 64. It hands over 64 at a time instead of one by one, which is a lot faster. You know, when your mom gets home with the groceries, you don't carry bag by bag. You load 15 bags onto each arm and walk into the kitchen. Right? This is essentially what we're doing there. Shuffle equals true. Again, scrambling the practice order each round so it can't learn anything from the sequence itself. And like we mentioned before, shuffle is off for the exam because the order doesn't matter for grading. And just to confirm that it is working, we can add a print statement down here. F train underscore ds images test when test underscore ds images. Okay, so this is just printing the tally to confirm it worked, right? So 10,000 practice photos, 2,000 exam photos, and half dogs in each. So again, we could run this right now. This one actually takes the longest to do because again, it's loading 60,000 photos and going through the training and exam sequences. So this one takes very long. You can run this if you want, but what I'm going to do is I'm going to go through all the code first and then run everything, and then I'll show you guys what it looks like when everything's all finished. So we can start with cell 4 now, which I'm going to title hiring the employee. So cell number 4 is basically about hiring an experienced employee, and you'll see what I mean in just a second when I type this out. Model equals model.resnet18. Weights equals, sorry, that should be all caps, image at 1k underscore v1. So what this does is it downloads an employee which has already studied millions of photographs of every kind of object. So it has very good eyes, so to speak. It knows what everything looks like, but it's not a dog expert. So this is, we're hiring the employee that really understands photos, right? Knows what legs look like, what fur looks like, what a snout is, what a mouth looks like. And we're going to be using that to create our own, essentially, dog expert. So we can move on now to for p in model dot parameters p dot requires underscore grad equals false. So this is basically telling it not to change anything you already know, right? So we lock in the experience that this model has. So when we're teaching it, it doesn't forget everything and become a clean slate, right? It uses what it already learns and builds on top of that. And it also makes the training a lot faster because there's a lot less to adjust here. Model.fc equals and then linear model.fc and underscore features 2. So this is the actual, if you want to call it, hiring decision. This program, it used to sort photos into 1,000 categories. We basically fire it from that job and say, we don't need you for that anymore, and we give it a new task, right? Stop sorting these photos into 1,000 different categories based on what they are. Either say it's a dog or not a dog, right? Only 2 possible answers. everything it knows about seeing and analyzing photos still stays. We're just adjusting its final decision. And model equals model dot to parentheses device. And this is just moving the model onto the fast chip, right? Again, we need the program and the photos in the same place, but moving both onto the GPU. Criterion equals n cross entropy loss. So this defines what counts as a mistake and how bad, right? So how models learn is by making decisions and seeing if they got them right or wrong, right? That's how humans learn. It punishes confident wrong answers a lot harder than uncertain ones, right? So if the model doesn't know and says, well, I'm not 100% sure, then it's, for a photo of a truck, let's say, then it's punished. But if it says, well, that's definitely a dog right there, I think that's a Clifford actually, that punishment is going to be a lot worse for the model. Model.fc parameters LR equals 1e minus 3. Oops. So this is the rule for how it improves, this optimizer. Right after each mistake, you adjust a little bit towards what would have been better, essentially. And this LR equals 1e minus 3 sets how big those adjustments are. And overall, you want it to be smaller steps, because moving way in the other direction after every single mistake, you're not really settling in a defined middle ground. So that's it for cell 4. Cell 5, title the real lesson. All right, so we're going to start with, sorry about that, epochs equals 3 for epoch in range, parentheses, epochs. So this is essentially telling the model to go through the whole pile of practice photos 3 times, right? Epochs equals 3, that's what that means. And one full pass is 1 round. We have model dot train running equals 0.0. So this is flipping the model into study mode, you could say, and it sets up a counter for how many mistakes it makes in a particular round. Then we have 4 images, labels in train underscore loader, images, labels equals images dot to device, labels dot to device. So those 2 lines are taking the next 64 photos and their true answers and putting them on the fast chip alongside the program. So again, photos, program, same chip. Remember that. Optimizer dot 0 underscore grad parentheses loss equals criterion model images labels loss dot backward optimizer dot step. So those 4 lines that I just typed out, starting with optimizer, these 4 right here, are pretty much the entire heart of machine learning. Everything else in this notebook is preparation and grading. So this does a couple things, right? First, we want to wipe the slate clean from the last batch. Show it the photos, the model guesses, it measures how wrong the model was, right? And it works out which direction each answer should have moved and nudge it a certain way. Then repeat thousands and thousands and thousands of times. So these 4 lines right here is adjusting the model. This is the learning part, essentially. This is how the machine learns, is by being nudged in the right direction after being measured how wrong it was, and just simply repeating and repeating and repeating and repeating and repeating. So those 4, you could argue that those are the 4 most important lines of this entire small project. So actually, I'm gonna do that just to really highlight them. Running loss dot item parentheses times images dot size 0. So this batch's mistakes to the running tally, right? There's a running tally of how incorrect or how wrong the model is. Obviously, we want that to decrease over the thousands of reps that the model is getting. So it's a good way to measure if the model is actually learning. Model dot eval correct equals total equals 0 with torch dot no underscore grad for images comma labels in test loader. Images labels equals images dot to device comma labels dot to device. Preds equals model parentheses images dot argmax 1. So these set up basically a pop quiz. Model eval, this right here, switches from study mode to test mode, right? And no grad means don't learn from these. It's simply a quiz. It's not more practice. And it's not letting it study the exam, right? So these photos are exam photos, but it's not letting the model learn from the photos itself, so they can't recognize them when they get them again on the exam, because that defeats the entire purpose. Whoa. Correct equals preds equals labels dot sum dot item total labels dot size parentheses 0. And finally our print statement, print f epoch +1 train loss running / lens len train underscore ds 3f here val accuracy correct / total 3f. So again, this is counting how many it got right out of how many it saw, and it prints the round's report. So how confused it still is on the practice material and what it scored on the quiz for each round, which, remember, we established a total number of 3 rounds. Now, we can move on to cell 6. And I said there were 7 cells, but the 7th cell includes a heat map, which I think is interesting. It's always interesting to visualize how the model perceives these images, but it's not required for it to work at all. All right, so you could finish this, you could do cell 6 and run it, and it would allow you to input an image, and it would spit out how confident it thinks it is a dog versus not dog. Dot metrics import. So cell 6 is really the actual report card. Right, it gets back to you of how well the model performed. Classification underscore report. So all this does is open a toolbox with better grading tools than just plain old what percent did it get right. Model.eval all underscore preds, comma, all underscore labels equals with torch.no grad for images, these labels in test loader, all preds dot extend model images dot to dot divide. Whoops, this should be bracket. There we go. Dot rmax 1 parentheses dot cpu dot numpy bracket, 2 brackets there, all underscore labels dot extend parentheses labels dot numpy parentheses double parentheses. So this is test mode again, and it goes through every exam photo and writes down 2 lists side by side, what the model guessed and what it actually was. And this little .cpu here moves the results off of the fast chip because the grading tools can't read from it, basically. So this is just a technical shuffle. Print confusion underscore matrix all labels, comma, all preds. Whoops. All preds. What the preds? Okay, there we go. Sorry. Technical difficulties. Classification underscore report, parentheses all labels, all preds, target underscore names equals not dog, dog. Double bracket. Okay, so now the model is working, and I'm actually going to say now that there are 8 cells. This cell 7, I'm going to put this in a completely separate cell because I think it's an important concept to try it on your own photo that you can upload from the internet. So that's what we're going to do in this. So if you want to do that, just stick around. This cell is not, it's going to be very short. Like I said, I had put this in cell 6 in my mind before, but I think the concept of it probably deserves its own cell. BIL, import image, uploaded equals files dot upload. But again, cell 6, this cell just prints the breakdown of how the model performed during its training and exams after, the thousands of rounds of training that it went through. And this cell 7 is just importing an upload tool for you to be able to find a picture on the internet, download it, put it in, and the model will give you an assessment of how confident or what percent it believes that it is a dog versus not a dog. So you'll be able to see that for an internet image that you chose, which I think is pretty cool. So all these 3 lines do is, again, open the toolboxes for uploading and opening imaging files. You'll notice that most of these cells, or even the process of this, starts with opening the toolbox first, importing models from the internet. So we're not building, everything from scratch, right? We have tools that we use to build greater things, or our own original things, right? We get the canvas, we get the paintbrush, we have the paint, right? We're not creating our own paint. We don't have to go out and chop wood to make the paintbrush or anything. We have all the tools. This is just us painting a picture that's our own and original using the tools that we are provided. So for name in uploaded, image equals image dot open name dot convert RGB x equals test underscore tf parentheses image parentheses dot unsqueeze 0 dot to device. So these 3 lines here, just open the photo, make sure it's in the standard color format, and runs it through the exam recipe from cell 2. It's the same size and color adjustment. This is preparing the photo that we upload to be similar to the ones that the model trained on, right? So it can give us a better accuracy rating. With torch.no underscore grad probs equals torch.softmax model x dim equals 1 bracket 0 bracket and print f name dog probs 1 percent bracket not dog probs 0 1%. So these 3 lines just show it the photo and ask for the score, and it'll return a score. So again, you'll be able to input an image and see something like whatever, 95% dog, 5% not dog. So you'll be able to see how the model scores your image and how well it works based on an image that you input yourself. So again, you could go to run all and this would work perfectly fine. You could find an image from the internet find an image of an animal, dog, or cat or whatever, and upload it and see if the model correctly labels it as either dog or not dog. But I think this next cell, cell 8, is very interesting because it's a really cool visual of how this all works. So if you would like that visual, you can follow along for this last cell, but like I mentioned, it's not necessary for the model to work. It works. Alright, so this is just the toolboxes again, opening numbers, the main box, and some math helpers, the drawing box, uploading, and image opening. So I think I mentioned it before, but this is going to lay out a heat map of the model's analysis of whatever photo you upload, and then show a basic graph showcasing its estimate for if the model is a dog, or if the image rather is a dog or not a dog. Okay, so those 4 lines are just the same as cell 7. It's a choose file button. You pick a photo, open it, run it through the exam recipe, and put it onto the fast chip. So this is it's the same setup as cell 7. It's just going to have this show this heat map once you upload the photo. And this is where we get into the heat map. Okay, so those 2 lines, they just set up 2 empty notepads and point at one specific spot deep inside the program, right, which is the last stage before it makes a decision. And that's the useful or important place to watch, because by then it's thinking about the entire object as a whole rather than just raw pixels, right? We don't want it to see it analyze a single pixel. We want it to look at how it's analyzing the image as a whole, which it's doing during that time. So that's why we're looking at that stage in particular. Now these two lines, they basically stick to recorders inside the program at that specific spot. So you can think of them kind of like security cameras, right? So the program doesn't behave very differently, but now everything that's passing through the point gets written down and analyzed. So this first camera, or H1, records what it noticed in the photo, and the second records how much each of those things mattered to the final answer, right? And that pairing is the whole idea behind the heat map. So these four, it's just test mode and then show it the photo, right? So as the photo passes through, camera one is recording. This softmax here, it converts the raw scores into percentages, and argmax notes which answer won, dog or not dog, so which had the higher percentage, essentially. Now, this is actually a pretty clever part of the program. So this backward right here, it basically asks the program which parts of what you saw would have changed your mind if they'd have been different, right? So working that out is exactly what it does during training when it's learning from a mistake. It learns what it analyzed and what would have adjusted its answer. And this camera 2 that we set up, it records the answer. So we get to see all of that. So that's pretty interesting. And that just takes the cameras back out. If you leave them in, they keep recording on every future photo, and things will start to clog up. So we just want to keep the pipe open and keep it flowing. So those two lines are just combining the two recordings. The first line, it takes the camera's recordings or notes to a single score, or it, it it reduces what the camera recorded down to a single important score for everything that the program noticed, and the second multiplies what it noticed by how much it mattered and adds it all up. So cam equals cam minus cam dot. So all that line does is rescale the result. So the lowest value becomes 0 and the highest value becomes 1. So this is just so the colors come out readable. That's all that's doing. All right. So originally the heat map comes out very coarse. It's a very small grid because the program thinks in broad regions as opposed to pixels. All that line does is stretches it smoothly up to the photo side so we can overlay it and really see what it's analyzing in a way that makes sense to us. So that's just resizing the original photo to match so the heat map lines up on top of it. I didn't reconnect there. There we go. So that line basically sets up a canvas with 3 panels side by side. And these next 3 lines are just going to be setting up each panel, essentially. Okay, so that's panel number 1 is going to be your photo, right? So it's going to show the photo you uploaded. Panel 2 is going to show the photo and the heat map on top of it, and then panel 3 is going to show up as a graph, like I mentioned before, 2 horizontal bars showing how confident it is either way that your photo is a dog or not a dog. So here we're going to set up panels 2 and 3. those two lines are for panel 2, and then we're going to set up panel 3 and tidy up the spacing and the display of all 3 panels, and we're completely done. So we're nearing the finish line of this project. Alright, so that's panel 3 all set up. And these last 2 lines, like I said before, just going to be tidying up the layout. Alright, so that's just tidying up the spacing and displaying all 3 panels. So we are officially done with the code here. Make sure that there's no typos. And now what we can do is, let's see, we can just get rid of that. Again, go through, make sure there are no typos, and assuming that there are no typos, when I click Run All, we're going to wait for it to run all the way through, and it depends what kind of hardware you have. For me, this typically takes an hour for the entire process, but at the end of it, something should pop up where you can get an image from the internet, upload it, and see the results. So we are going to jump to that now. I'm going to run all, and if there are any errors in the code, I will let you all know. But yeah, I'm going to click run all here and jump to when everything has been pushed through, and we can finally test this thing out and see how it works. Everything has been executed. We are now on the penultimate cell here. It's waiting for me to upload an image. As you can see, everything went good here. One typo that I made, that if you were copying what I wrote, I put model.resnet instead of models, which will stop the program. Again, it's an easy fix. It'll tell you how to fix it, no problem. Another thing to watch is some indentations, especially with this cell. A couple of these I made in the binary dog class, so they didn't register fully, so make sure that they are outside here and everything's indented correctly. But if you make sure all that's good, you should see it says train 10,000 images, test 2,000 images. We go down here, epoch 1 or round 1, value accuracy was about 88%. Round 2, the value accuracy was about 89%, and round 3, the value accuracy was about 87%. So hovering around the 90% area, which is good for a bare bones model like this. Again, this shows all the matrix calculations here. And here, before we get to see the heat map, we're just going to make sure that everything's good. So I've taken the liberty of searching up an animal. I'm searching up a panther, and I will take this image of a panther, and I will save it as Black Panther .jpg. You want to make sure that these are all .jpg, so when you're renaming them, just rename them to .jpg. As you can see, I've downloaded some other animals here as well. So we go over to choose files, and of the many animals that I have downloaded, I'm going to select this Black Panther here and press open. And as you can see, it returns the results of not dog 93.6%, which is exactly what we're looking for. Obviously, a panther is not a dog, so that's perfect. Now we go down to the fun part, which is the heat map. So again, I'm going to choose file, and I actually downloaded another panther image that I like a little better. So I'm going to use that one, and we're going to see what the model thinks. Is it a dog or not? Let's see. So again, as you can see, the confidence went slightly down, but still 90% sure that this is not a dog. And you can see the model analysis with the heat map where the model looked, mostly this area, right? Mostly the face, which would give it away. This is not a dog-like face. Again, this is the image that we uploaded, and here's the confidence score with the two graphs. So very interesting. And if you want to do this again, all you do is press this button again and it resets. I'll do a couple more just to show you. I'll do this elephant here. See what it thinks. Again, model analysis, 92% sure. Higher confidence rating at this is not going to be a dog. Mostly analyze the body of the elephant. And now let's give it a dog and see how it performs. So here's a nice image of a dog, golden retriever. Let's see what it thinks. Ooh, okay. So this is something that you may run into. Again, forward-facing dog. The image was it was analyzing the pixels, not really analyzing the animal, and it actually got it wrong, right? You can tell it's not sure. It's almost a 50-50 split, but 55% says not dog, which is going to happen, and that's okay. With a model like this, we're just trying to understand the concept behind it. These things can always be improved. Let's see if we can give it an image of a dog that it gets right. So let's go. I cleverly named this cat. So if the model was somehow reading the names of the files, it would be tricked. So let's upload this, and there we go. All right, the model's analyzing the portions that we want it to analyze, mostly the face, not really looking at the environment, and it's about 60% sure that this is a dog. What we can draw from these few uploaded images is that the model is a lot better at identifying things that are not dogs and things that are dogs. And that's probably because the dog set is a lot smaller than the non-dog set. In other words, there are a lot of different things out there, and dog is one category out of thousands of categories of objects that it could be. So let's give it one more image. Let's give it a cheetah and see what it thinks. Okay, see, this is interesting. This is why it's helpful to have a heat map. Again, 96% sure it's not a dog, which is true. But when we look at the heat map, we notice that it probably got confused by this tree branch here and thought that this tree branch was the subject of the image, which it's obviously not. Not a lot of analysis of the cheetah, which is interesting. So it got it right, but maybe not for the right reasons. And that could come back to bite us in the future if we didn't have that information. So let's give it one more test. Let's give it a camel. Let's see how it does. Okay, analyzing the legs of the camel, which is fair, and 98% sure that it's not a dog, which is correct. So there you have it. There is our basic machine learning, very bare bones model. Is it a dog or is it not? Yeah, does not take that long to build. It's not very complicated, but the concept of learning this stuff is very important because it can be applied to many different fields, whether it's recognizing signs of tumors in people. There are a lot of different medical applications, engineering applications, which is why this has really been a thing for a while and is still, still being used more and more today in the world. So I hope that this video gave you some satisfaction of being able to build something from scratch, something interesting hopefully, and gave you a better understanding of what machine learning is, how it works, the materials that we input, and what we get out of it. So thank you for watching. This has been building a machine learning model from scratch.